Hello guys, welcome to another discussion. So in this video we are going to break down this paper. We'll discuss it and give all the explanations for why the answers are what we say the answers are. So this is a chemistry SDA paper 3 2022 paper. Okay, so try to follow along. Where you're confused, you can just ask in the comments section there. All right, let's just get into it. Now the first question says a list of names of gases is given. So just remember, this is the structure for most of the paper threads. You are given a group of substances and then you are to use those to answer the following questions. Okay, so you should be familiar with some common compounds in chemistry. So what you can do is just to, with your notebook, you can just write common compounds that you'll come across, write short notes on those, and then it's easier for you to approach such questions because this is like 1, 2, 3, 4, 5, 6, 6 free marks. Okay. All right. So the first question, like I said, a list of names of gases is given. We have propane, ammonia, nitrogen, carbon dioxide, propene, and carbon monoxide. The instruction says use the list to answer questions A to F. Each name can be used once, more than once, or not at all. State the name of the gas which, let's start with the first one. A contains only one type of atom. Contains only one type of atom. Okay, so maybe just to quickly do that, remember propane, that is a hydrocarbon. So it's carbon and hydrogen. Same with propene. So those are two different atoms. Next, ammonia, that's NH3. Nitrogen, that's N2. Remember, it exists as a diatom. Okay, then carbon dioxide, that's CO2. Then carbon monoxide, that's CO. So the answer there is going to be this guy here, nitrogen. B says is an unsaturated hydrocarbon. What is an unsaturated hydrocarbon? Remember, an unsaturated hydrocarbon, for our syllabus, we look at a group of compounds, the hydrocarbons that have a carbon-carbon double bond. Okay, so that qualifies it to be an unsaturated. Remember, unsaturated, it means that you can take this double bond, convert it into a single bond, create an extra space to bond or add other substances to that particular compound. So the answer there is going to be propene. Okay, propene. So here we have propene, and then the saturated or the opposite hydrocarbon there will be propane. Okay, they have single bonds. C says dissolves in water to form an aqueous solution that gives a green precipitate when added to iron 2 chloride solution. All right, so this is going to be familiar when you remember your test for ions. Okay, test for ions. What reagents do we use there? Remember, when you're doing the practical paper, we usually use sodium hydroxide. Okay, and what else? We also use ammonium hydroxide. Okay, ammonium hydroxide. Now, from the list above there, we don't have anything related to sodium hydroxide. Okay, but we do have something that can give us this, because remember, whatever substance that we have amongst this list here is going to first dissolve in water. Okay, so how does that happen? In order for us to get ammonium hydroxide, we start off with ammonia. Okay, the gas. So NH3 is going to dissolve in H2O to form ammonium hydroxide. Okay, ammonium hydroxide. So that's how we get this guy. Now this is used to test for metal ions. Okay, so in this reaction here, that means the NH4OH will be reacting with what? Will be added to iron 2 chloride. Okay, iron 2 chloride. Okay, what's going to happen there is that the hydroxide comes here okay, and then the Cl goes to the other side, okay. And then when you remember your solubility rules, you know that all ammonium salts are soluble. So therefore, NH4Cl is going to be soluble, and then the iron hydroxide is going to be insoluble. Hence, it comes out as a precipitate. And then remember, one more property of transition metals is that they form colorful compounds. Okay, so this gives us a what? A green. Maybe ironically, let's just use a green color, So this gives us what? A green precipitate. Okay, all right. So that's the explanation behind that. So our answer for C is going to be ammonia. Okay, ammonia. So here we have ammonia gas. D says reduces iron 3 oxide to ion in the blast furnace. Remember, the reaction in the blast furnace is that you have this ion O, Fe2O3 plus what? Carbon monoxide. Remember, in the blast furnace, it's a controlled environment where higher temperatures favor the production of carbon monoxide instead of the carbon dioxide. The carbon monoxide, remember, is coming from the burning of our coke, or the coal, the cured coal that we're using in the blast furnace. And then this is going to reduce that to Fe plus carbon dioxide. Okay, carbon dioxide. So the answer there is going to be carbon monoxide. Sorry, yeah, carbon monoxide. Carbon monoxide. All right, let's continue. Next, the question says, is produced when a strong base is added to ammonium chloride. Okay, now this is the reaction between ammonium salts. This is an ammonium salt and a strong base. For example, let's say you have sodium hydroxide, which is going to be a strong base, plus ammonium chloride, NH4Cl. Okay, now this reaction here, you're going to get water, a salt, and ammonia gas. Okay, and ammonia gas. So you get your water, H2O, plus a salt. The salt is going to be sodium, is going to take this ion. Okay, so it's going to be the sodium chloride. That's the salt. And then these two here will form the NH3. Okay, the NH3, which is the ammonium what? Ammonium gas. Okay, so that's the reaction there. So this is a special case reaction for strong base and ammonium salts. So you need to remember that you produce ammonia gas there. Ammonia gas. F says dissolves in water to form an acidic solution. Now what's going to do that is going to be carbon dioxide. Okay, because remember, when you go back to the grouping of your oxides, we said that this guy here, carbon dioxide, it's an acidic oxide. Okay, it's an acidic oxide. So whenever it encounters, or when it dissolves in water, it will form an acidic solution. Okay, it will form an acidic solution. So CO, let's not write it that way. Carbon dioxide. Then the other thing, remember, this is one of the compounds that will give us acid rain. Okay, this is one of the compounds that will give us acid rain. In that topic, when we're discussing the formation of hardness in water. Okay, so carbon dioxide plays a role there. So just always remember the smaller details so that you can be able to understand the compound in more detail. Okay, question 8 says, a redox reaction occurs when ion filings are added to aqueous copper 2 sulfate solution. The equation of the reaction is shown there. Okay, so that's a full complete reaction equation there. A Roman figure 1 says, state one observation that would be made during the reaction. Okay, now remember, whenever you have a reaction, you look at the products that are produced. Okay, you compare what you started off with and what you ended up with. So you use those. Okay, every time you produce a gas as one of your products, then the observation is going to be production of bubbles or effervescence. And then when you're producing a solid, if you know the characteristic of that solid, you can state. But since here we started off with the solid and then we have another solid here, you can't just say the formation of a solid. Okay, you can only give that observation when it's an instance like electrolysis, whereby you create something out of a liquid. Okay, but in this instance you can't use formation of a solid as an observation because already the solid was there. Okay, so nothing changed in a way. But if there is a color change, then you can say that that is going to be the observation. And then the other thing, you look at your solutions. Now the solution, the solution color of copper 2 sulfate is not similar to the solution color of iron 2 sulfate, so you can comment on that. Okay, so those are the two main observations that we have. So we'll start with the solids there. So iron filings are more silver colored, and then copper is more pink brown. Okay, so we can just say formation of a pink brown solid. Remember, you can't say it's copper because you didn't really test for it. Okay, you didn't, there's no test here, there's no step way or procedure where we tested that solid. So you can't just blindly say it's copper because you haven't done any metal test on the solid. Then the next one is going to be the color. Remember, copper 2 sulfate is blue in color, whereas this guy is going to be clear in color. So our solution, reaction solution, or just the solution color changes from what to what? From blue to clear or colorless. Okay, clear or colorless. So I'm running out of space there, so I had to borrow this area here. Name an oxidizing agent from the equation. Name an oxidizing agent from the equation. Now, how do we know an oxidizing agent? Now, the way I want you guys to remember, you can just use this box here. Okay, so now your oxidizing agent versus your reducing agent. Okay, so I'm just using the initials there. OA for oxidizing agent, RA for reducing agent. Now, what we do here, we know that oxidizing agents are reduced and then your reducing agents are oxidized. It's more like you're swapping them like that. Okay, so this is the best way to remember it for those that have a hard time remembering the difference between oxidizing agents and reducing agents. Okay, so we go ahead and analyze that equation. Okay, let's go ahead and analyze that equation. We know that Fe changes to what? To Fe2 plus. Okay, because now it's in this compound here, that means it has formed an ionic compound. So when you form ionic compound, do you lose electrons or you gain electrons? Remember, you lose electrons. Okay, so we write the electrons this side. Now if this thing is losing electrons, we use our oil rig to try to remember what losing electrons is. Now oxidation is loss of electrons. Okay, oxidation is loss of electrons. So if oxidation is loss of electrons, that means what? So we have Fe is going to be tied to oxidation. Now there are only two things there. Okay, so the other one is the iron, the other one is the copper 2 sulfate. Okay, so that means the copper 2 sulfate is going to be this side. Okay, CuSO4. Okay, so that means name an oxidizing agent. Okay, so that means our oxidizing agent is going to be the copper 2 sulfate. Okay, the copper 2 sulfate. Okay, our oxidizing agent, it's an oxidizing agent because it does what? It takes electrons from other substances. Okay, so now remember, the copper changes from copper to ions by gaining electrons from where? From this guy to form copper atoms. Now you do that by gaining an electron. That means oxidizing agent, remember, they take electrons from other substances. Okay, all right, let's just remove all this explanation. I hope it helps. Remember, we just don't answer the questions, we also explain why the answers are what they are. Next, the question says, in another experiment, excess ion filings are reacted with 30.0 cubic centimeters of 0.150 mole per cubic decimeter sulfuric acid as shown by the equation. So we have the equation there. Ion reacts with sulfuric acid to form what? Iron 2 sulfate and hydrogen gas. Okay, now this is a typical reaction between metals and an acid, which is an exothermic reaction. Okay, let's just get to the question. Problem figure 1, calculate the number of moles of sulfuric acid contained in 30.0 cubic centimeters of 0.150 mole per cubic decimeter. Now you see that the units that you have here in the concentration, you have cubic decimeter for volume, whilst the volume that you are using there, it's in cubic centimeter. So you need to change this guy into that, not the other way around. Okay, not the other way around. Okay, so that's one thing we have to look at. Now, what formula are we going to use? Normally, I prefer for us to draw these legal triangles to help us remember the formulas. But if you know them, it's fine. Okay, you can just write them right away. So N here, and then concentration, and then volume here. Okay, then volume here. Because remember, concentration is what? This is the formula. The formula is just here. So this is the concentration. From this, you can get the formula. You know that concentration is equal to, these are moles, N for moles, okay? N for moles over, this is what? This is volume. Now that's the formula. And then just rework it whenever you come across a problem. All right, so what are we looking for? We are looking for moles. Therefore, N is equal to concentration times volume, which is equal to, concentration is 0.150 mole per cubic decimeter times, remember, we're going to divide this by 1,000 to change it to what? To change it to cubic decimeter. Okay, to change it to cubic decimeter. So I'm just going to do it once in the equation here. 30.0 cubic centimeter divided by 1,000 cubic centimeter, and then now this has been changed to cubic decimeter. Okay, because this cancels that, and then the decimeter cancels the other decimeter, and then you punch that into the calculator, and then you get 0.0045 moles. Okay, the units are regular. Okay, moles. On to the next one, Roman figure 2. Use the answer to be Roman figure 1 and the equation to calculate the number of moles of iron 2 sulfate that were produced. Now, what's happening? What's happening is that we go back to the equation. Okay, we go back to the equation. Now, this equation here, we're going to use a ratio of reactants. Okay, remember, in a chemical equation, no mass is created or destroyed. Now, for us to form this product here, we're going to be using what? We're going to be using particles of these two substances. No new particle is going to be created during the creation of the product. So this is the principle of mass conservation in a chemical equation. Therefore, we use a ratio of reactions. All right, so let's take the sulfuric acid the way it is. Okay, if there was a 2 here, you take it with that 2, but this time around there's no 2, so the coefficient there is just a 1. Okay, so H2SO4 is 2. What are we looking for? We are looking for SF ESO4. Okay, now what are the coefficients? We know that if you don't have anything here, it's just the 1. If you don't have anything here, it's just the 1. Okay, now we found moles for sulfuric acid, so we write it on the sulfuric acid side. Remember, this is just the simple ratio. Okay, it's 2x. This is supposed to be 5. Let's just write this properly. Okay, just a second. 4. Okay, 0.045 is 2x. So your x is going to be 0.0045. Since the ratio of reaction is 1:1. Okay, so they're going to have the same number of moles. Roman figure 3 says calculate the mass of iron 2 sulfate produced during the reaction. Okay, now we write our triangle again. Okay, let's draw our triangle again. All right, so remember mass here, AR or MR. AR if you are dealing with individual atoms of the same element, and then MR if you are dealing with a compound. And then here we're going to have N for moles. What are we looking for? We are looking for mass. Mass is given by MR in our case times N. MR is given here 152 times N. We found N above there 0.0045. Always double check your numbers. So if you put an extra 0 here, you get the answer wrong. Okay, because these marks or these numbers, the answers that you get in the previous questions are forwarded to the next one. Okay, all right, so this gives us 0.684 grams, because it's mass. Remember, it's mass. All right, so then we continue. Roman figure 4 says the percentage yield of iron 2 sulfate obtained was 80.3%. Okay, I use the answer to be Roman figure 3 and the percentage yield to calculate the actual mass of iron 2 sulfate produced. Okay, so this is simple. Remember how we get our percentage yield. We say that the actual mass, I'm just going to abbreviate, actual mass over the theoretical mass. The theoretical mass is the mass that we get when you are doing the calculations in your book, okay? Not you actually measuring in the lab. So that is the theoretical mass. Multiplied by 100, remember, percent means out of 100. You get your percentage yield, okay? Yield. And then here we just substitute everything. So actual mass is going to multiply by 100 over theoretical mass. What are we looking for? We are looking for the actual mass, okay? So this is going to be 100 actual mass over theoretical mass is equals to 80.3. Of course, there are other shortcuts that you can use, okay? Because you know that percentage, the 8.3 is out of 100, you can already do that. I'm supposed to substitute here. Yeah, but remember, the way we teach this is so that even the slowest learner can appreciate how everything is found. But if you know a trick or two, use that, it's fine. All right, so theoretical mass is what we found there, 0.684. Okay, so you just multiply by the 0.684 both sides, multiply 0.684 both sides, and then you divide by this 100 here to get your final answer. So therefore actual mass is equals to, so all this divided by 100. Okay, so you punch that into the calculator. What do we get? Get 0.5472 grams. Okay, always follow the significance figures that are given at the instruction page there. Okay, so that's the actual mass. Now a trick here is that for most of the experiments, or for most of this type of questions, the actual mass, the actual mass is usually smaller than the theoretical mass, okay? Because in the lab, whenever you are doing your experiments, you lose some of those particles when you are rinsing your apparatus, when you spill accidentally, when they evaporate, things like that. So therefore, the actual mass is usually smaller than the theoretical mass. But there are instances where you can get the other way around, but for the most part, okay? Let's continue. 9 says, naphtha is one of the fractions obtained from crude oil. State the name of the process used to obtain naphtha from crude oil. Remember, it's fractional distillation, okay? Fractional distillation. Okay. B says naphtha contains a saturated hydrocarbon with the formula C12H26. Describe a test to show that the hydrocarbon is saturated. How do we test for saturation? Now remember, we use the test, we use bromine water, and then what are the results? Now remember that bromine water is red brown in color, okay? So whenever you have a saturated hydrocarbon, that bromine water will not react with the hydrocarbon, so it just stays that color, okay? So bromine water remains the same, okay? Water remains, so it doesn't change because there is no chemical reaction that's going to take place. Remains red brown. So we're just putting the color there so that the examiner can acknowledge that we know what color bromine water is, okay? Bromine water remains red brown for saturated hydrocarbons, okay? Hydrocarbons, simple as that. Roman figure 2 says 1 mole of the hydrocarbon, the one that we are given here, can be cracked to form 1 mole of an alkane and 4 moles of ethene. So in other words, this guy here, C12H26, remember, cracking is where you break down a large molecular hydrocarbon and then into smaller hydrocarbon chains, right? Okay, so we have 1 mole again. So this is 1 mole, okay? This is 1 mole. So we have 1 mole of an alkene, and then so CH, so this is just going to be 1, and 4 moles of ethene. Do we know the chemical formula of ethene? Yes, we know that because we know how to generate the compound, okay? We know how to generate the compound. So for us to do that, we need to remember how you get what? How you get, so how you get the chemical formula of the compounds, okay? So for you to get the chemical compounds of an alkene, you're going to use C, so it's going to be CnH2n, okay? And then for this guy, you use CnH2n plus 2. That's how you generate that. Just to remind you. But we know that ethene is going to be what? It's going to be 2 carbons. So 2, you put a 2 here. So that's 2. And then 2 times 2, that's 4. H4. Okay. Let me just clear this. Okay. Now, what's the next step? Remember, we are to find that the formula of the alkene, okay, this guy here. We know that generally it's CH, but we don't know the other numbers. Now, since we know these, we can just go ahead and multiply out those numbers so that we get the total number of carbon atoms that we have there, the hydrogen atoms that we have there. So we multiply. So it's going to be 4 times this. So you get C, 4 times 2 is going to be 8. and then 4 times the other 4 is going to be H16. Okay, now we come back here to this guy and then we subtract so that we found the missing carbons and hydrogens. So it's C8H16. Okay, so if we subtract, you get a 10 here, H10, then you get C4. Then this is going to be the formula then. So it's C4H10. All right. Show your wiki. Now remember it says show your wiki. So let's just go ahead and write it nicely without a lot of this space used. Okay, so let's now write it more in a smart way. So we're just going to say we work with what we have. Okay, so 4 moles of, let's expand this, of C2H4 gives us what? So this gives us C8H16. Then we go ahead and say C, so this is the first part, C12H26 minus the C8H16. Okay, so we get our C excuse me, C4H10. So this is how we found the formula. Okay, so that's our working there. Remember, the other parts I was just explaining so that you understand or remember, the general formulas and whatnot. Let's continue. Ethene reacts with chlorine to form an organic compound X. Draw the structure of organic compound X. Okay, so let's just explain what's happening. So ethene, remember ethene, it's C2H4. Now let's draw that. So this is going to be, remember it's an alkene, so it has that double bond. Okay, it has that double bond. Okay, so it looks like this. So this guy reacts with what? With chlorine. Chlorine, remember, it's Cl2, which structurally it will look like this. So during the chemical reaction, what's going to happen is that this double bond changes into what? Into a single bond. Okay, changes into a single bond so that you get something like this. You get C, single bond to another C, and then now this is the original hydrogen that we had. We had how many hydrogens? 4 hydrogens. And then these chlorines here, okay, they break under the influence of light, and then they bond into that extra space that was created. So this becomes Cl, that is Cl. Okay, so the question asked us to draw the structure of the compound X. So you're just going to draw what this here. This is just the explanation. You are drawing that. C says ethene can undergo addition polymerization to form polyethene. Okay, what is that? Define the term addition polymerization. Remember, it's a process by which small molecules, okay, small molecules, we call them what? Molecules called monomers join to form long chained molecules called polymers. Okay, called polymers. Simple as that. Roman figure 2 says state the property of polyethylene that makes it a pollution problem. Remember, these compounds are the ones that we use for the plastic materials that we have, your plastic cups, your shopping bags, etc., etc. Now the problem with these long chains is that they are non-biodegradable. Okay, non-biodegradable. degradable. The question is, what does that mean? It simply means that this group of compounds cannot be microbially broken down into simpler molecules, so they remain like that for a very long time. Okay, 10 says fluorine is a group 7 element. It can react with sodium metal to form sodium fluoride. Construct a balanced chemical equation for the reaction between fluorine and sodium metal. Remember the checkpoints for our chemical equations. 1 is the correct chemical symbols. 2 is going to be what? It's going to be the state symbols, and then lastly the balancing. Okay, so let's quickly do that. We'll start with what? With fluorine. Fluorine is F. You can check your periodic table. Okay, you can check your periodic table. Remember the periodic table is given here. Where's the periodic table? Yeah, this is the periodic table. So F there for fluorine. So the periodic table is given at the end. So don't fail because you didn't see the periodic table. Okay, F. Now remember, group 7 elements exist naturally as diatom. So this is going to be F2 plus sodium metal remain a monoatom, so it's just Na. Now what do we get? Sodium fluoride, NaF, because Na it's plus and then F it's minus, so they just combine like that. All right, so next, the state symbol. So fluorine is a gas at room temperature and pressure, while sodium is a solid metal at room temperature and pressure. Then the compound they form, it's a salt, is going to be a solid salt. Okay, so solid. Okay, then the next thing is balancing. Now we have 2 fluorines on the left side and then we have 1, so we need to make that 2. So let's balance that. So we put a 2 here. Now we misbalanced the sodium, so we need to correct it on the opposite side. So here we put another 2. That way everything now is balanced. Then we can collect the 3 marks. Fluorine reacts with hydrogen to form hydrogen fluoride, HF. State the name of the type of bonding in hydrogen fluoride. Remember, we have 2 types of bonding: ionic bonding, no, actually 3: ionic bonding, covalent bonding, and what? And metallic bonding. So here, what we have here is going to be covalent bonding, because in this scenario hydrogen is acting, or it's behaving like a non-metal. Okay, behaving like a non-metal. Draw a cross and dot diagram to show the bonding in hydrogen fluoride. Show all the electrons. Now when it says show all the electron shells, you must show all the electron shells. Now let's just start with the configuration. Hydrogen is 1, so the configuration is just 1, and then fluorine is 9, so the configuration is going to be 2, 7. Okay, so that's the configuration. All right, so let's just draw the cross and dot diagram. We'll start with the nucleus, H, to acknowledge the nucleus, and then 1 ring there. Okay, then for fluorine, it's going to be F, and then the first shell has 2 electrons. So I'm going to choose crosses for fluorine, and then the next one, which is going to be sharing there, will have harmine. So remember, hydrogen is going to bring 1, and then fluorine is going to bring 1. Okay, so we have an X and a what? And a dot. The dot is coming from the hydrogen. Okay, then the next one we gave so that's -1. We're left with what? With 6 electrons on the fluorine. Okay, so that is going to be the answer. Explain why the melting point of sodium fluoride compares with that of hydrogen fluoride. Remember, we are comparing these two. Okay, So if we're comparing them, we should be using comparing resin weights. Okay, we use comparison mode. Okay, so we know that Na sodium fluoride has a higher, so we're just comparing them right at the start, and then we can give reasons for that. Okay, or the explanation. Has a higher melting point than, you can write the full words there, so that you don't get lost, than hydrogen fluoride. Okay, now we state our reasons why that is the case. Okay, because sodium fluoride has strong electrostatic forces, while hydrogen fluoride has weak electron no has weak intermolecular forces holding the molecules together. Okay, then we get the full marks. Okay, now let's explain this before we part ways. Okay, so remember that sodium fluoride is an ionic compound. Okay, so this guy Fe, this guy NaF, is a what? This guy is an ionic compound. So that means you have Na plus and F minus. Now this difference between the plus and negative is giving us an electrostatic force. Okay, so that the bonding here is going to be very strong. So you need a high amounts of energy to separate the sodium from the fluorine. Okay, or from the fluoride ion. Whereas in the case of HF, hydrogen fluoride, what's happening here is that you have two types of bonds. So between the H and the F, you have these intramolecular forces. Okay, so these ones are not the ones that are broken when we are melting things. Okay, or when we are dealing with the melting and boiling points of things. The ones that are broken are the ones that exist between one molecule to the next molecule. Okay, one molecule to the next molecule. Now between two HF molecules exist weaker intermolecular forces. Okay, intermolecular forces. So like HF, So now this is going to be attracted to the next one by this weaker intermolecular forces. Now these intermolecular forces are the ones that are keeping this thing together. Then when you hit this, okay, we break this. These are the bonds that we break. Okay, let's say you started off with hydrogen fluoride as a solid. What's going to happen is that these forces are going to be stronger, very strong in the case of a solid. Then as you hit them, the substance up, some of these forces are broken, but not all of them, because it will remain a liquid at some point, then a gas. Now in gases, that's why you have the least strength for the intermolecular forces. Okay, all right, thank you guys for tuning in. I'll see you on the next one. Don't forget to like and give the video a thumbs up so that we keep creating more content like this. Road to 1K, guys. Road to 1K. Thank you.